Data engineering has been caught in a structural compromise between the fluid iteration of local data science and the rigid grid of enterprise data warehousing. At the local level, data scientists prioritize speed and flexibility. They rely on Python, Pandas data frames, and flat files like CSVs to rapidly explore data and test hypotheses without waiting for infrastructure to provision. But local exploration does not scale. When that data needs to be operationalized, engineers require ACID guarantees, concurrency, and massive compute power. This historically forces the data out of local scripts and into heavy client-server data warehouse architectures. The friction occurs in the translation. Moving a simple analytical query from a local laptop to a production server requires defining rigid schemas, explicitly mapping every data type, and configuring network permissions just to ask a basic question. This split screen illustrates that exact bottleneck. To ingest a compressed dataset on the left, a traditional database like Postgres demands significant manual configuration, spelling out every integer and varchar before you can write a query. On the right, DuckDB takes a completely different path. It automatically downloads the file, decompresses it in memory, infers the schema, and executes the query instantly. DuckDB is a modern open-source SQL engine. Crucially, it is an in-process online analytical processing, or OLAP, database. It was built specifically to merge the reliability of a strict database with the low-friction flexibility of local file manipulation. By embedding warehouse-grade analytical processing directly inside the local application environment, we bypass the immense complexity, network overhead, and heavy compute costs associated with distributed systems like Apache Spark. To understand how a single local node can achieve warehouse-level speed, we have to look at the physical storage layer, specifically how the data is laid out on the disk itself. The historical standard for databases is a row-based format. This layout is optimized for online transaction processing, which excels at adding, updating, or deleting single records one at a time. In a row-based system, a single record's distinct fields, like the date of a train ride, the station name, and the length of the delay, are written physically adjacent to each other on the storage medium. In row-based storage, to calculate average train delays, the CPU scans massive blocks of irrelevant fields, like date and station, just to extract the target metric. The solution is columnar storage, like Parquet. The physical layout pivots, storing all identical data fields together continuously. Grouping identical data types allows the CPU to selectively scan only the requested column, drastically reducing disk I/O. This contiguous layout also enables high-efficiency compression. Instead of 100,000 identical dates, run-length encoding stores the value once with a multiplier, shrinking the physical footprint. Memory layout dictates I/O efficiency. Transitioning from row-based scanning to selective columnar access is the first step to achieving analytical speed locally. Once the physical read strategy is optimized, the execution architecture of the database engine itself becomes the next limiting factor. This illustrates the traditional client-server database model that dictates most enterprise pipelines. The application logic and the database engine live on separate servers, communicating across a network protocol. This architecture incurs steep performance penalties. Data must be retrieved by the server, serialized for transport, pushed across the network with inherent latency, and then deserialized by the client. These continuous communications waste vast compute cycles before query logic is even applied. DuckDB solves this with an in-process deployment model. The database server node shrinks down and embeds directly into the host application itself. Running strictly inside the host application's memory space completely eliminates the network transport gap and all associated data serialization overhead. We can see this advantage clearly in Python environments. DuckDB uses a mechanism called replacement scan. When it encounters a Pandas data frame, it executes a zero-copy read, latching directly onto the data exactly where it sits in memory without duplicating it. Because Pandas is restricted to a single thread, it creates a processing bottleneck. DuckDB's zero-copy access allows it to apply its own highly parallelized SQL engine directly over that single-threaded Pandas memory structure. Eliminating network serialization and memory duplication unlocks the full parallel compute potential of multi-core processors, transforming a standard laptop into a hyper-efficient analytical engine. But local RAM is finite. The question becomes how these mechanics scale when the dataset reaches 10 terabytes, vastly exceeding available local memory. Modern hardware provides part of the answer. NVMe solid-state drives offer massive data throughput, meaning processing a 10 terabyte dataset locally is physically possible if the system avoids I/O bottlenecks. Raw disk speed is insufficient alone. To process data at that scale locally, the engine must aggressively avoid reading the vast majority of the payload. DuckDB achieves this by implementing lightweight indexing across chunks of the dataset. This diagram shows a Parquet dataset split into distinct, manageable blocks called row groups, containing roughly 100,000 rows each. DuckDB automatically calculates and attaches lightweight metadata tags to each block. By tracking minimum and maximum values, the engine builds a metadata map to execute predicate pushdown. Querying delays over 2 minutes? It evaluates metadata first. Row group 1's max is 1.6 minutes, so it ignores it entirely, proceeding directly to row group 2. Intelligent metadata evaluation and aggressive I/O skipping, not just sheer hardware power, is the mathematical mechanism that allows consumer hardware to process terabytes of data without crashing. While this single-node architecture provides extreme local efficiency, it introduces steep operational limitations when integrated into a broader enterprise environment. DuckDB's primary operational bottleneck is that it is strictly designed as a single-player experience. Mechanically, this happens because a single active writer places a strict lock on the entire database file. While multiple clients can read a file simultaneously, the moment one user writes an update, all other concurrent access is blocked. Furthermore, single database files become physically unwieldy at enterprise scale. Storing a 20 terabyte analytical history in a single local file is entirely impractical for distributed engineering teams to manage or share. The industry's answer to decoupling storage from compute for distributed teams is the lakehouse architecture. The foundation of a lakehouse relies on object storage, like Amazon S3, which provides infinitely scalable, incredibly cheap, and fault-tolerant remote file hosting. But raw object storage has a critical operational flaw. The files are immutable. Once written, they cannot be updated. This makes standard transactional deletes, row updates, and concurrency impossible out of the box. Without an intermediary system to manage the metadata and coordinate write sequences, raw object storage simply cannot support the strict ACID guarantees required by modern data pipelines. To bridge the gap between local columnar compute performance and distributed cloud storage scale, a new architecture has emerged, DuckLake. This setup maps the architecture. At the base, we have immutable Parquet files residing remotely in an S3 data lake. At the top, multiple isolated DuckDB clients run locally. The critical innovation is dropping a lightweight database, like Postgres, into the middle layer. This middle database serves as a centralized catalog layer. Instead of acting as a file system lock, the catalog manages a versioned manifest of pointer addresses to specific Parquet files on S3. This catalog database never touches the raw data. When a client performs a write, Postgres creates a new snapshot entry in its transaction log and points to new Parquet files. Concurrent readers are simply directed to the previous stable snapshot until the write transaction is committed. Because the lock is now a managed database transaction in Postgres rather than a file system level block, multiple isolated DuckDB clients can coordinate updates without interference. This decoupled catalog enables a true multiplayer environment for highly parallelized local engines, allowing teams to share a single source of truth across a distributed object store. Managing the transaction log in this way makes possible advanced lakehouse capabilities on top of raw object storage, such as evolving schemas on the fly, or executing time travel queries to access historical dataset states. This modular setup provides the exact capabilities of proprietary cloud data warehouses, but completely avoids their massive operational overhead and vendor lock-in. By perfectly aligning physical hardware realities with smart columnar indexing, in-process execution, and a decoupled catalog layer, analytical data engineering achieves enterprise concurrency and maximum scalability at a fraction of historical costs.